Alright, hello everyone. I wanted to make this video as another review material as you study and prepare for the geometry test on Monday. So the way that this is going to be designed is I'm going to give you a problem and you can pause the video. So like for example, I have my work covered up with this scrap sheet of paper, but you can pause the video and then try the problem on your own. Alright, so in this particular problem, you would be being asked to find the length of line segment AD and the length of line segment DC, given what you observe in the figure, and also given that the length of AC is equal to 12. So if you want to give it a go, pause the video, and then check back here in a second. Okay, so the first step here to solve is to define AD as x, and then defining DC as 12 minus x. Now, you could swap these. You could say DC is x and AD is 12 minus x. Either way works fine. The important concept here, though, is that we recognize the length of AC is equal to 12, and through the segment addition postulate, we know AD plus DC equals AC, and so then therefore I can make these numerical statements with respect to defining a new variable x. So that's my first step. Now, my second step from here is to recognize what theorem I'm going to be needing to use to solve this problem. And I recognize here that I have angle B is bisected by line segment BD. And through this, I recognize that I am using the triangle angle bisector theorem, such that we know AB is going, AB is as to AD, AB is to AD, as is BC is as to DC, or we can also write it out like this. So we can say AB is to AD is as BC is to DC. Or we could also write it, if you prefer, in this notation. So that's sort of my first step. The dots filled in a little bit simpler. There we go. Now we recognize this theorem, we recognize this proportion, and from recognizing that, I can substitute in my values for AB, AD, BC, and DC. A helpful hint when you're tackling these sorts of problems, whenever you see an angle bisector within a triangle, usually that's a good clue that we're going to be using the triangle angle bisector theorem, okay? So again, recognizing what theorem to use, setting up the proportion, and then substituting in the values. From there, all we're doing is, I'll scooch it up a bit, all we're doing is algebra, cross multiplying and simplifying down for x, which is the length of AD, I got 24/7. And then to calculate the length of DC, I take DC equals, and I'm just substituting it back into my formula, 12 minus 24/7 equals 60/7. Now, earlier in the course, we derived this proof, or excuse me, we derived this theorem, the triangle angle bisector theorem. But sort of at this stage in the game, since we have a fundamental understanding of how and why the theorem works, you don't necessarily feel the need to go through and write the entire proof where we went on and did extra constructions. So this would be an example of, we know the theorem, we proved it, we understand how it works. Now that we have that deeper knowledge of what's going on, now we can apply it to problems like this. Okay. Or if you want to think of it simply, you could say this is to that is as this is to that, or bing bing bang bang, whatever works for you. I've heard it said a lot of different ways. Okay, let's take a look at our next problem. All right, so I see here that I'm working with right triangle ABC. I'm given the hypotenuse length BC as 80, and I'm given one of the leg lengths, in this case AB, is 25. Well, before I do anything, I always like to fill in any math problem, you always want to fill in information that is possible to be filled in from the given information. So what I mean by that is, well, I can clearly define or calculate the length of AC because I know I'm working with a right triangle, okay? And so using Pythagorean, we find that AC is equal to root 5,775, which I recognized could be split up into root 25 times root 231, which then leaves me with 5 root 231, or 5 times the root of 231. When you have a large value in your radicand, it's a good idea to test, say, okay, I'll divide this by 4, divide by 9, and so on and so forth. And so, like in this case, you only had to go up and divide by 29, which isn't too, or excuse me, 25, which isn't too bad. Okay. So I've calculated the length of AC is 231. Now, this problem is actually very similar to the problem we just covered. The only difference here is that it didn't explicitly give us AC. We had to do a calculation to calculate it. Now, same business as the last problem. I'm going to go ahead and define AD as x and line segment DC as 5 times the root of 231 minus x, which will probably make that a quantity. And again, I'm using the triangle angle bisector theorem, and I can make this statement that AB is to AD is as BC is to BD. Oh, and I already have it there. Perfect. Now I can substitute in my values. 25 is to x, as is 80 is to quantity 5 root 231 minus x. Cross multiplication. Now here, this is kind of a good review of working with radicals. So I have 25 times the quantity, 5 root 231 minus x, and quantity. Through the distributive property, I think maybe a good way to remember this or internalize it is, think of this 5 sort of as like the coefficient, if you will. And so, like, if you had 25 times 5x, then you would just be multiplying 25 and 5. So you get 125x. So for some people, that I think that can help. So we're left with 125 root 231 minus 25x. I get the x on one side of the equation by adding 25x to both sides, resulting in 105x equals 125 root 231. Divide both sides by the quantity of 105, which results in x equals 25 over 21 times root 231. I reduced 125 and 105 and kept the root 231, and that's equal to AD. Now I just need to plug that back into my DC formula, which I kind of did this by hand, where I got a common denominator and went on like that. And I found that DC is equal to 80 over 21 times root 231. So these two problems, this first one and this one, are actually fairly similar in nature, in that we're using the angle bisector theorem, triangle angle bisector theorem. Just this second one, the information was not as explicitly given. Okay. Now for our last problem. Sorry, let me get this adjusted. Okay, there we go. So in this problem, we're actually going to, well, take a second first, obviously, and see if you can solve it. The objective here is to solve for the length of z, or from here to here. I didn't label all of the points. Okay, so this problem is working with the side splitter theorem, or you could say the corollary to the side splitter theorem. What's important to notice here is this. So we have these 3 parallel lines, but realistically, I could kind of redraw this triangle such that I have this. Sorry, my artistic skills are not that apt. Okay. I know that these, like, this whole line, this is a line, right? So from here to here, plus here to here, plus here to here, equals the whole value of here to here. or I can say here to here plus here to here equals here to here. So I can say, like, I'm kind of, I don't want to say removing this parallel line, but I'm redrawing it. And I think that this will make it a bit easier to see. And this whole length right here, from here to here, is 70, right? And so I can see here that I can use side splitter theorem. I can say z is to 12, as is 12 is to quantity 70 minus 12, right? So, like, even though we don't know specifically, like, if we were to label this x and y, it's okay, because we can we can make this statement, so to say. I'm trying to think of the best way to explain it. Or we can understand this figure in this context. And so from that, we can set up the proportion, and then just the rest is solving for z. What's important to recognize here is the corollary to the side splitter theorem is in essence just saying this. So if we have these parallel lines, sorry, one second. It's not perfect, but anyway, all we're saying here is we're building off the side splitter theorem. Okay, so like if we have A, B, C, X, Y, Z, and these are like the side lengths, right? And I guess you could even extend this to be a triangle. You have a fourth line there. But the general idea here is, before we were just kind of working with, I'll draw it up here. If you had this, A, B, X, Y, we were saying A is to B as is X is to Y. And we're just sort of building off that. A is to B as is X is to Y, B is to C as is Y is to Z, and so on and so forth. So if you remember in class, there was that one day where I said, well, technically you could have like an infinite amount of parallel lines squeezed in here, right? So it's sort of just building from this idea of the basic side splitter theorem. And I was going to say too, this proof right here, or this statement A to B as is X to Y. Remember, we also too, we went through and derived that one. We went through and talked about how we can make that proof for that theorem, or how we can justify making this statement. So anyway, I think that these three problems are good practice problems. They kind of tie in some of the theorems we've been using. And I guess last word of advice, as given to me a while ago, whenever you're doing anything with numbers, always look to see if you can first fill in any missing information. So like if the figure, or if the problem has given you some information, see if you can build off of it. And then after that, always look to set up equations. In math, if you can set up an equation of any form, or of any type, you're on the right track. It's a good way to start. So anyway, I hope this video is helpful, and thanks for watching. Bye.